for this delay. I mean, there was a misunderstanding about something. With these examples, and this is on, again, on omega convex set, and it's called semi-Apollonian metric. Did I talk about this yesterday? I just wrote the name. Okay, because I think I said the name. Okay, so this is defined in the following way. We have 2 points, x and y, and I want to define the distance between x and y, and this is the supremum. You see, we had defined a distance like this when we take the point B and so on. Now this is different. I take a point A. I take a point A in the boundary, and I take the supremum over A in the boundary of omega of the distance from x to A divided by the distance from y to A. Now, unlike the previous examples I gave, the triangle inequality is trivially satisfied here because I'm taking supremum over A and oui, pardon. Yes, okay. There is a logarithm. Thank you. Well, yes. Well, let's put it here. Boundary of omega. No, I want to put it there. I want to put it there. I want to put it there. I want to put it there because now it's the triangle inequality is satisfied because the supremum of the sum, I mean, it behaves well with respect to the sum. So this is the definition, and why is this interesting? I mean, you have to prove a few properties of this metric to see that it makes sense, that it's interesting. And let me tell you 1 or 2 properties of this. So yes, we talked about the Finsler structure of the Hilbert metric. We talked about the Finsler structure of the Funk metric, and I explained to you more or less why they are Finsler. So I don't know whether this is a Finsler metric. This is a question. It's not obvious to me that it is Finsler, and I never thought. I mean, I never spent any time to answer this question. So if somebody wants to think about this, okay, this is one thing. The second thing, where is this? Okay, the second thing I want to tell you is about. You see, we have these metrics defined for arbitrary convex sets, and we want to see what they give in special cases of convex sets, because we have in mind the Hilbert metric that in the special case of the disk gives the Klein model of hyperbolic geometry. So what is this in the case of the disk, the open disk? So let's say in the two-dimensional case. So here you can, I will give you the answer, and you will check it by yourself. Well, this is the log of this quantity here. I have a half here, half of the log, and this is x minus y. This is x bar, the complex conjugate of x, and this is x minus y bar minus x minus y. I think this is the formula. This is the formula. You have an explicit formula here. And what is nice is that the symmetrization, in fact, the arithmetic symmetrization of the semi-Apollonian metric of the disk, this is, I don't want to, I mean, you can do the exercise, and I don't want to write the formula. The thing is that this is the Poincaré metric of the disk, which is, yes, the complex conjugates. Why is it positive? This one, you mean? I don't know. I mean, you have to think about it. It is positive. Yes, it is positive. This is a special case of this is positive. Sorry, did I make a mistake here? Plus x. Yeah, I'm not so good in formulas. Maybe something is some. Let me give you. Okay, I can correct this later, but so this is the S delta is the Poincaré metric of the disk, and the another thing in the case of the upper half plane. So this is something we talked about it. This is something we talked about yesterday. Let me write this new formula. Which I hope is correct this time. So this is the log of this is y minus x bar plus y minus x, and this is x minus x bar, which should not be also correct. Here, this is okay, and this, yes, but I don't like this x minus x. Okay. Put two bars around. Yes, yes. Put two bars around what? Here? Bar of the whole denominator. Bar of the full denominator. Yeah. Full denominator. The full denominator. This is the full denominator. What do you mean? You want to put something more? Yes, I think I want to put something more, but I didn't copy it correctly. I don't want to. I mean, in fact, I don't care about the formulas. the important thing is that S delta in this case of the upper half of the upper half plane is the upper half plane. In the case of the upper half plane, gives you the Poincaré metric. This is the statement. I don't want to correct the formulas. I don't want. I hate formulas. Yes. For what? Yeah, different domains. Yes. 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 No. No. Yeah, I don't know. I don't know. I mean, this thing does not follow from the other. This thing here does not follow from the. This thing here does not follow from this one. I mean, you must. It's really a chance, you know. I mean, there's no obvious reason. I don't find any obvious reason. By the way, this is in a paper with Mark Troyanov. We wrote this a few years ago. So this is one thing why this metric is. I mean, you can relate it to some familiar metrics, so it becomes more interesting. The second thing, in fact, is that this metric here. I just want to mention. I mentioned something about Thurston metric on Teichmüller space. For those who know this thing, in the case of the torus, in the case of genus 1, the Teichmüller space is just the Euclidean. I mean, one of these Euclidean models of the hyperbolic space. I mean, it's just a hyperbolic space, and it turns out that this non-symmetric metric here on the disk is Thurston's metric on the Teichmüller space of the disk of the torus. Okay, this is also why this is interesting. So this is another example. I'm sorry for this confusion here. Maybe somebody can check the paper and then tell me in this case before. Yes. So what is here? Here x minus something. Is this in the case of the upper half plane or in the disk? In your because we have the two formulas, one for the upper half plane and one for the disk. Upper half plane. Okay, so this is for the second. Yes. So here I have to put what?
X minus y bar and x minus y.
X minus y. Okay.
And x minus y bar.
Yes.
Minus
X minus y. Okay. X minus y bar minus x minus y. Okay, thank you. So this is the formula. I copied this from our paper, and I'm always bad in copying. Okay, so this is at least in the case of the upper half plane, and then I think you can correct the other one which I wrote for the disk. The next thing in the same spirit of what we talked yesterday about in the case of the Funk metric, the next thing is to study the geodesics of this metric. The geodesics geodesics of this metric You want to tell me something else? Okay, the geodesics of this metric. And for this, I know only one answer, in fact. I know only one answer. In the case of the, in the case where omega is the disk. In the case where omega is the disk. And I know that the geodesics I know that the geodesics of the hyperbolic metric are geodesics for this non-symmetric metric. This is what I know. Just in this case of the disk, and this is also in our paper. I don't know in the general case, not because it's difficult, but because I never spent a time on this. So if somebody wants to study the geodesics, say for an ellipse or for a triangle or for a half a disk or something like that, and study the uniqueness of the geodesics starting at a point and going to some other point. I think this is this should be feasible. Okay. Yes. Not now. I mean, for what I said, there are no conditions at all on the boundary. No, it's a convex set. Yes, it's a convex set, so the boundary is homeomorphic to a circle or to a sphere if you are in n dimensions. So another thing is that the formula I gave, the formula I erased here, which was wrong at the beginning, I don't know what it gives in higher dimensions. There should be a formula like this. There should be a formula like this, but the important thing is that we know that that it coincides with the Poincaré metric is something valid in all dimensions. But regarding the formulas, I don't know. So the next thing I want to say about the which I could say about the previous ones is the previous examples is to study the isometries of this metric. And I don't know anything about the isometries of this one. I don't know anything, in fact, about the isometries of the Funk metric, which I gave you. Okay? The full question of the isometries of the Hilbert metric was solved very recently, in fact, maybe 3 or 4 years ago. It's very recent compared to I would say, about 100 years, a little bit more than 100 years, where this metric was invented by Hilbert. It's not very difficult. I mean, just because it's not a very difficult result. I mean, it took 100 years to prove it, but it's not a very difficult, I think, because not many people were interested in proving it. Yes. No. I mean, there's no direct relation. There's no direct relation. Yes, there's no direct relation. Okay, so this is also the question of the isometries. Yeah, and then the question. I mean, just again to relate to the course, the lectures by Courtois and Besson. This is the question of the boundary at infinity, or a related question whether it is delta hyperbolic or not, delta hyperbolicity. So there are a lot of boundary definitions of boundary. The best thing is that you take the visual boundary, or the Boseman boundary, the horocycle boundary, and so on, and then you want to relate this, and you want to I mean, if you know that the space is delta hyperbolic, then there is a canonical boundary. This is the Gromov boundary. If you don't know that it's delta hyperbolic, then you can study the visual boundary at each point and try to characterize and show, for instance, that the visual boundary is this boundary which you see, this boundary of the convex set, or if you have to identify some points and so on. I mean, the question is also about the geodesics of this metric. It's related to the question of the geodesics of this metric, whether the geodesics whether all these geodesics, I mean, whether this space of geodesics starting at a point describes the boundary or not, or whether there are geodesics which stay at the bounded distance. Okay, so this is the next example, and now my next example is a series of examples. It concerns all these examples which I talked about, but from a different point of view, which is the following. So again, now I have here a convex set. And I think I want to call now omega the exterior of this convex set. The exterior of the convex set, and I want to define a distance between 2 points x and y in the exterior of the convex set. So again, this subject was started by Boseman in the 1960s. He wrote a paper called Time-like Metrics. He was motivated by the geometry underlying general relativity, and I will talk about this later. But so time-like metrics. And then there were two students of Boseman who worked and published papers about this. One is called Beam, I think, like this. Another one called WOO, W-O-O. And apart from these three papers, in fact, I don't know any paper on this subject. So this is a subject which was stagnant for several decades. And then recently I wrote a paper, in fact, with my co-author Yamada. I think the paper is also called Time-like Metrics, and then you can also find it. It just appeared, and I think there are some. I mean, I'm saying this because I think there are some not too difficult questions. You see, it's not a subject where you have hundreds of people working on the same problem, so you are in competition with all of them and so on. This is a subject which is still not very crowded. It's a good subject for students. I mean, students and also other people. Let me mention also something. I mentioned Boseman. There's a parallel theory. By Alexandrov, whom many of you know his work, the famous Alexandrov. In fact, there are two famous Alexandrov. This is A.D. Alexandrov, which many of you know. And Alexandrov, and in fact, contrarily to Busemann, Alexandrov had many students, maybe 20 students, working on similar things, not exactly this, but similar things. I will tell you the difference. And Alexandrov called this chronogeometry. If you Google chronogeometry, you will find some papers. It's more or less the same word. You see, the time and chronos is the same word. In Greek, chronos means time. Time-like geometry. So let me give you the idea. You have 2 points in the exterior of this convex set, and you want to define a distance between x and y, or a distance from x to y, and you want to imitate something which you know, right? We want to imitate some reasonable distance for convex sets. So the first thing is that you want to imitate the Funk metric. So you get something called the Funk time-like metric. I will tell you why it is time-like. You have x and y, and then you want to extend the ray starting from x, passing through y, and you get this point B here. And you say that, well, this is my Funk metric, but the time-like Funk metric. This is f of xy. This is the log of the Euclidean distance from x to b divided by the Euclidean distance from y to b. Okay? And now what do you do with this? Yes? Yes, this is a good question. What is if there is no such b? So this is defined on a subset of, let's say, omega cross omega. I define it only on the points where this ray hits B. If it does not hit B, if it does not hit B like this, then you don't define the metric. You don't define the distance. And this is interesting because I said there's a relation with physics, with relativity. So it is like in physics, in general relativity, you can define the distance between one point and another point if the second point is in the future of the first point. If not, the distance cannot be defined. There's a restriction here. There's a physical restriction because of the speed of light. Things cannot travel less with a velocity less than the speed of light, and so on. I mean, this is formally a time-like metric. A time-like metric is a space, say, omega. Here, omega is the exterior of this disk, equipped with an order relation. Let's call it, let's denote it like this, an order relation. And a distance function So I called it f here because it's the time-like Funk metric, but here I want to take the general case. So this is rho, where rho is defined only if and only if, in fact, x well, is less or equal to y, and this means either x is equal to y or x is less than y with respect to this order relation. With respect to this order relation. And then, I don't want to enter into this, but let me just mention for those who know a little bit the work of Boozman, and then with several conditions, plus several, let's say, axioms on, well, let's say on this and this and their relation. For instance, one of the axioms will tell you that for every point x in your space and every neighborhood of x, you have 2 points, y and y prime, such that y less than x less than y prime. Something natural, you know, like he wants axioms for existence of geodesics, existence locally of geodesics. So what is a geodesic here in such a space? It's just a geodesic is just a map gamma from an interval into, well, omega, satisfying rho of xy equals rho of xz plus rho of zy for every well, x, z, y in, yes, just a minute. So where is the mistake? Is this correct? Somebody said something? So, okay, so it's the same definition of a geodesic in the usual case. I have here the definition of a geodesic. So there's a triangle equality. And something important which I didn't tell you. So among these several axioms, there's this axiom that rho satisfies not the triangle inequality, but the reverse triangle inequality. I don't have gamma. This is rho. xy equals rho of xz plus rho of zy. Yes, for every. Yes. Yeah, this is not the order relation. This is not my order relation. This is, you see, there's a confusion here between x, y, and z in here. X, y, and z here. X. Yes. Yes, this is gamma. Yes, thank you. Gamma. Yes, the same mistake as I did yesterday. This is gamma because of this confusion here between points x, y, z in the space and points x, y, z in my so this is gamma. Well, yes. You want me to write this again correctly? Yes.
Can we replace this interval AB by any complete order set?
Well, I want you can replace it by. No. There is use. I'm using. I want. In fact, what I want is. Okay. Let me write this because I want this relation to stand only for points. So this is an interval. This is an arbitrary interval in R. Okay? This is an arbitrary interval in R. And I want here, let's take other, so T1, T2, T3. Now this is the order relation in R. Okay? When I have this, I want rho of gamma T1, gamma T3 is equal to rho of gamma T1 plus rho of gamma T2 plus rho of gamma T2, gamma T3, and this is now yes. So this is for any. You see, I want. So when I consider there's now the order relation of my space which enters, because when I consider this path, I want any 2 points on the image to be any 2 points here, and now I can put x, y. I want y to be in the future of x. These are the only I only consider such arcs. Okay.
This R can be replaced by any ordered field.
The R can be replaced by any ordered pair.
Ordered field.
Ordered what?
Field.
Ordered field. Probably yes. Probably yes. Probably yes. But I don't know. I don't know. So anyway, so rho satisfies. So rho satisfies. Rho this satisfies. This is the important thing now. That rho satisfies. That rho satisfies this time-like inequality or time inequality. Time inequality instead of the triangle inequality. I have the time inequality, and the time inequality says. So again, as before. Now we take rho xy. This is greater than rho xz plus rho zy. And now here, this is for any x, y, z satisfying, well, x less than y, x less than z, and z less than y. You see, there's a confusion here because I'm using here this relation for the relation between real numbers, whereas I'm using the same relation with for my order relation there. But I think you understand. Yes. Okay. So this plays the role of the triangle inequality. And yesterday I asked you to prove the triangle inequality for the Funk metric. Did anyone do this? Did anyone try to do this? Yes. Did you know how to do it? Did you manage to do it? Okay. You want to do it here? Okay. Go ahead. So she will. Why is this
zero
true?
or positive number, it will be either 0 or positive. If it is 0, then these are equal, and if it is positive, then
Yes. So this x minus a. Yes, I think it's true. It's not. I have never thought about this proof. I think it is true. Okay, it's good. Okay, we will talk about this later. Okay, you want to copy it here? Okay, so go ahead.
I've written this generally. Forget it. Forget it. I have written it generally. The matrix I have written for this x, y, and b. Now I am taking this to be a, b, and c. X, y, z from omega, and we have to prove that fxy is less than or equal to fxz plus fzy. For this we have to solve right hand side, which is fxz plus fzy, and what is this? This is log of xz, x minus a upon z minus a. And what is this? Zy. Fzy is log of z minus b upon y minus b. Here we use the property of log, which is log m plus log n is log mn, x minus a, z minus a into z minus b upon y minus b. And again we'll use property of log, which is log x minus a, y minus b plus log z minus b, z minus a. Now either this is positive or this is 0. So here we get this is greater than or equal to log x minus a, sorry, No, sir, I think there is a problem in the proof.
Yes, I see. Yes, in fact, I guess this can be less than 0, right? Z minus b. When you wrote that this is greater than 0,
This is less than 0 how?
So it can be less than 0. It can be less than 0. Because z minus b, you don't know where it's at. Z minus b can be less than.
And here is
z
a
minus
mod.
a.
Here is a mod.
Yes, I know. No, it's not. It's that this ratio here can be less than 1.
Oh, less than
This
1.
is it. This is the problem.
I thought there is a problem in the proof.
Yeah, okay. So
Okay.
anyhow, I'm really very glad that you tried.
Okay, sorry, sir.
Okay,
I'm
no,
sorry.
It's good. So I want somebody else to think about the proof of this because I mean it's a good exercise. Anyway, there is a proof of this. There is a proof of this in Hilbert's book, The Foundations of Geometry. He has an appendix. I think it's one of the later editions, maybe edition number 6. You know that there are several editions. He published several editions of this book, maybe 10 editions. During 10 or 15 years, on the span of all these years, he published several editions because in one of the editions, he has a proof of the triangle inequality, but for the Hilbert metric. But the proof of the triangle inequality for the Hilbert metric works also for the triangle inequality of the Funk metric, the same proof. You must be careful about the order of the elements. Hilbert of x and y is equal to Hilbert of y and x, but not the Funk of x and y. So one possibility is to look into this book, but you can try to do it in another way. Anyway, so here the same proof, but adapted. The same proof of the triangle inequality for the Funk metric will give you a proof. I mean, you have to change some of the signs. You see, because there's some convexity inside, whereas here there's some concaveness. In fact, maybe next time I'll tell you the answer if nobody gives the proof. Proves the time inequality. The time inequality for the time like Funk metric. Okay, so if you find the proof for the other one, you will find the proof for this. Now I want to say something about the Finsler structure. You remember I showed you that the Finsler structure of the Funk metric is the tautological metric that you have a family of norms on this open set, which are the different translations of this convex set omega. Now here you have something new. Something new, which is in fact time-like Finsler structure. Time-like Finsler structure. So what is a time-like Finsler structure? As we said, a Finsler structure allows you to measure lengths of paths, lengths of arcs in your space. Okay, so time-like Finsler structure allows you also to measure lengths of paths in your space, but I have a time-like space, and I want to talk only about, well, time paths, that is admissible paths, admissible paths are these paths where any point in the I gave the definition before. In fact, I didn't use this terminology, but I want only paths where when I have 2 points x and y here on the image of the path, and with the right orientation, this path has some orientation which comes from the orientation of the interval in R, then y is in the future of x. So, for instance, in my example of the time-like Funk, this path like this is not an admissible path because I have a point here, I have a point here, which follow each other in the image of the image of the path, of the map defining the path, but y is not in the future of x. This path here. Well, no, let's take it like this. Less wiggle. This one here is a time-like path, because if I take a point here and any point y, then they stay in the future of each other. Okay? I don't want to write the formal definition, but everybody understands what is an admissible path. I want every point in the future with respect to this orientation of my R to be in the future in the formal definition of my. And I want to measure the length of this path. So I need some kind of norm in each vector, in each tangent space, that will allow me to measure the length of the vectors, right? Okay. And we remember that in the case of the Funk metric, the norm just came from the convex set itself. That is the boundary of that convex set was the unit ball of my norm. So here we have the same thing. Except that I want to use now. I mean, just from looking at this example, you can get the idea. You have time-like norm. So the time-like Finsler structure will be defined by a time-like norm in each tangent space. And what is a time-like norm? A time-like norm, in fact, it's like a norm, but instead of the convexity, of the norm function, I want it to be concave. And then concaveness will imply that the triangle inequality is in the reverse sense. Okay? So more formally, a time-like norm on a vector space V is a function defined on a cone C, while in fact I want to take here an open cone, and I want to take a proper cone. I will tell you what proper means. You see, the idea is the following. This cone for the Funk metric, this cone at a point, I want it to be this visible part of my convex set. This is my cone, and I want to be able to measure the length of the vectors that are only in this cone. Okay? So I have a function defined on an open and proper cone. Proper cone means there exists a hyperplane. There exists a hyperplane through the origin which contains the cone in one of its sides. That is, you see, this is a proper cone because I have a hyperplane here. I have a line where the cone is contained in one side. This is not a proper cone. This is not a proper cone. This is the origin. This is not a proper cone because this is not a proper cone because for every line here, I cannot find a line such that the cone is contained in one side of this line. Okay. So everything is motivated by this example. So we have an open proper cone, and then this function is the function f. F satisfies defined on an open cone. I want to include the origin here, such that f of 0, well, f of 0 is 0. F of lambda x equals lambda times f of x. So these are the usual properties of a norm. This is for every lambda positive. And the third property is that concaveness property. Instead of convexity, I have concaveness. So this is, say, f of tx plus 1 minus t y. This is greater than t f of x plus 1 minus t f of y, and this is for any t strictly between 0 and 1. This is the concaveness property.
So,
yes.
is this property, corresponding to Hessian of the Finsler function, square of the Finsler function negative? Negative definite?
Yes, exact. Yes. If you want to study, there's no differentiability here, but in the case you mentioned, yes, this is in the case of the usual norms, the Hessian will be positive definite, and in this case it will be negative definite. Yes. So when you have such a definition and such a setting, then any example you have in mind, or any theory you have in mind, which about some Finsler manifold, you may try to find the analog in this setting. Okay, this is also a good problem, I think. So I have here I can with this definition, you see, you can immediately find the corresponding theorems which I proved last time for the Funk metric. For instance, the geodesics. You see, the geodesics. So, if you have an admissible Euclidean segment, admissible in the sense I defined before. An admissible Euclidean segment, it is geodesic for this time-like Funke metric. If you have some defect of strict convexity, some Euclidean segment in the boundary of your convex set, then you have a defect of uniqueness of geodesics by the same construction we saw yesterday for the usual Funke metric. You can show that this Funke metric is this Funke time-like metric is the tautological Funke metric, is the tautological Finsler geometry for this theory of time-like Finsler structures. And then the next thing you want to define is the analog of the Hilbert metric. Analog of the Hilbert metric. So you want to define a time-like Hilbert metric. So, well, you remember that in the other case, I will finish in 2 minutes. Yes. In the case we studied, in the classical case, we have x and y, and the Funke distance between them, and we define the Hilbert metric as the symmetrization, that is the Funke distance from x to y plus the Funke distance from y to x, right? So here we have to do something. We have to do something analog. We have to invent something because I have x and y. I can define the Funke distance between x and y, the time-like Funke distance. But if I do y and x, then I have nothing to hit, right? So you introduce two, instead of one, you introduce a theory with two convex sets. For instance, this one here, and this one here now. You see, so this was our Earth, and this was the outside space, the space around us. But now you want to imagine that there's another planet there, and you want to say that, well, a Hilbert metric is associated to this convex set C1, which is the future, and this convex set C2, which is the past. And then you want to define a distance. You want to define the distance on pairs, only on pairs x and y, such that the line from x to y hits C1, and the line from y to x hits C2, which is the past. So you work with this kind of geometry, and now you want to define again the time inequality for this new distance. This new distance, which is this one plus this one. There's a small subtlety, but you can define it, and then you want to show that this is a Finsler. Well, a time-like Finsler. Which is possible. In fact, it turns out it is possible. And then you see there are instances which I will talk about this next time. There are instances where you don't need to have two convex sets. And this is if you work on the sphere say, on the two-dimensional sphere, but it could be on the n-dimensional sphere. So look here on this sphere, I have let's call it C, my convex set, and then omega is the exterior of my convex set. Now, if I take 2 points here, x and y, such that x, the line from x to y hits C, then I have the line from y to x. The line from y to x, if I extend it here in my example, it will hit C again. So there's a setting like this in spherical geometry, which I will try to explain next time, where this becomes a very interesting example on the sphere. This is one thing. The last thing I want to say is that I never tried to find time-like analogs of that semi-Apollonian metric, which I defined at the beginning. You see, instead of defining the Funk metric, you take 2 points here, x and y, and then you want to define. I already forgot. So I want to put this sup before the log. So this is the sup of the log of x minus a divided by y minus a prime. So here I want to take all the a's here. A is in this part, which is the visible part of the convex set, the visible part as seen from x. Okay? And for y, there's a visible part which is seen from y, which is here. You see? You have to deal with this. You have to decide whether you want. So if I take y in the visible cone from x, then the visible part seen from y contains the visible part seen from x. See, if I take here, there's some geometry of concave sets which you have to deal with. Anyway, this is something which I never tried to figure out. This is a time-like semi-Apollonian, which if somebody has time and has the will, he can or she can study this. And I think I defined another metric also, which I don't remember. Yeah, this the metric I call the weak semi-hyperbolic. Yes, there should be a time-like analog of this. I mean, there are a lot of questions here.